10 papers. 1. Polydendriform structure on faces of hypergraph polytopes. We extend the works of Lode-Ronco and Burgunder-Ronco on the tridendriform decomposition of the shuffle product on the faces of associahedra and permutohedra, to other families of nestohedra, including simplices, hypercubes, and yet other less-known families. We also extend the shuffle product to take more than two arguments, and define accordingly a new algebraic structure that we call polydendriform, from which the original tridendriform equations can be crisply synthesized. 2. Zoology of non-Hermitian spectra and their graph topology. We uncover the very rich graph topology of generic bounded non-Hermitian spectra, distinct from the topology of conventional band invariants and complex spectral winding. The graph configuration of complex spectra are characterized by the algebraic structures of their corresponding energy dispersions, drawing new, intimate links between combinatorial graph theory, algebraic geometry, and non-Hermitian band topology. Spectral graphs that are conformally related belong to the same equivalence class, and are characterized by emergent symmetries not necessarily present in the physical Hamiltonian. The simplest class encompasses well-known examples, such as the Hattano-Nelson and non-Hermitian SSH models, while more sophisticated classes represent novel, multi-component models with interesting spectral graphs resembling stars, flowers, and insects. With recent, rapid advancements in metamaterials, ultra-cold atomic lattices, and quantum circuits, it is now feasible to not only experimentally realize such esoteric spectra, but also investigate the non-Hermitian flat bands and anomalous responses straddling transitions between different spectral graph topologies. 3. Perverse Sheaves, nilpotent Hessenberg varieties, and the modular law. We consider generalizations of the Springer resolution of the nilpotent cone of a simple Lie algebra by replacing the cotangent bundle with certain other vector bundles over the flag variety. We show that the analog of the Springer sheaf has as direct summons only intersection cohomology sheaves that arise in the Springer correspondence. The fibers of these general maps are nilpotent Hessenberg varieties, and we build on the techniques established by De Concini, Lustig, and Procesi to study their geometry. For example, we show that these fibers have vanishing cohomology in odd degrees. This leads to several implications for the dual picture, where we consider maps that generalize the Grothendieck-Springer resolution of the whole Lie algebra. In particular, we are able to prove a conjecture of Brosnan. As we vary the maps, the cohomology of the corresponding nilpotent Hessenberg varieties often satisfy a relation we call the geometric modular law, which also has origins in the work of De Concini, Lustig, and Procesi. We connect this relation in type A with the combinatorial modular law defined by Guillet-Paquet that is satisfied by certain symmetric functions, and deduce some consequences of that connection. 4. Non-perturbative negative geometries, amplitudes at strong coupling, and the Amplituhedron. The Amplituhedron determines scattering amplitudes in planar n equals 4 super Yang-Mills by a single positive geometry in the space of kinematic and loop variables. We study a closely related definition of the Amplituhedron for the simplest case of four-particle scattering, given as a sum over complementary negative geometries, which provides a natural geometric understanding of the exponentiation of infrared divergences, as well as a new geometric definition of an IR finite observable f of G and Z, dually interpreted as the expectation value of the null polygonal Wilson loop with a single Lagrangian insertion which is directly determined by these negative geometries. This provides a long-sought direct link between canonical forms for positive, negative geometries, and a completely IR finite post-loop integration observable depending on a single kinematical variable z, from which the cusp anomalous dimension can also be straightforwardly obtained. 5. An effective weighted K-stability condition for polytopes and semisimple principal toric fibrations. The second author has shown that existence of extremal Kähler metrics on semisimple principal toric fibrations is equivalent to a notion of weighted uniform K-stability, read off from the moment polytope. The purpose of this article is to prove various sufficient conditions of weighted uniform K-stability, which can be checked effectively, and explore the low-dimensional new examples of extremal Kähler metrics it provides. 6. Non-Abelian Majorana fermions in topological S-wave Fermi superfluids. By solving the Bogolyubov-de Gennes equations analytically, we derive the fermionic zero modes satisfying the Majorana property that exists in vortices of a two-dimensional S-wave Fermi superfluid, with spin-orbit coupling and Zeeman spin splitting. We calculate the energy splitting due to Majorana hybridization and identify that the S-wave Majorana vortices obey non-abelian statistics. 7. Minimal non-abelian nodal braiding in ideal metamaterials. Exploring new topological phases and phenomena has become a vital topic in condensed matter physics and material sciences. It is generally believed that a pair of band nodes with opposite topological charges will annihilate after a collision. Recent studies reveal that a braided colliding nodal pair can be stabilized in a multigap system with PT or C2ZT symmetry. Beyond the conventional single-gap abelian band topology, this intriguing phenomenon exemplifies non-abelian topological charges. Here we construct ideal acoustic metamaterials to realize non-abelian braiding with the fewest band nodes. We experimentally observe an elegant but non-trivial nodal braiding process, including nodes creation, braiding, collision, and repulsion, that is, failure to annihilate, and measure the mirror eigenvalues to elucidate the essential braiding consequence. The latter, at the level of wave functions, is of prime importance since the braiding physics essentially aims to entangle multiband wave functions. Furthermore, we experimentally unveil the highly intricate correspondence between the edge responses and the bulk non-abelian charges. Notably, all our experimental data perfectly reproduce our numerical simulations. Our findings pave the way for developing non-abelian topological physics that is still in its infancy. 8. Periodic points and arithmetic degrees of certain birational self-maps. Consider a cohomologically hyperbolic birational self-map defined over the algebraic numbers, for example a birational self-map in dimension 2 with the first dynamical degree greater than 1, or in dimension 3 with the first and the second dynamical degrees distinct. We give a boundedness result about the heights of its periodic points. This is motivated by a conjecture of Silverman for affine automorphisms. We also study the Kawaguchi-Silverman conjecture concerning the dynamical and the arithmetic degrees for birational self-maps in dimension 2. In particular, we reduce the problem to the dynamical Mordell-Lang conjecture and verify the Kawaguchi-Silverman conjecture for some new cases. 9. Contact invariance of Q-Gorenstein toric contact manifolds, the Ehrhart polynomial, and Chen-Ruan cohomology. Q-Gorenstein toric contact manifolds provide an interesting class of examples of contact manifolds with torsion first Chern class. They are completely determined by certain rational convex polytopes, called toric diagrams, and arise both as links of toric isolated singularities and as prequantizations of monotone toric symplectic orbifolds. In this paper we show how the cylindrical contact homology invariants of a Q-Gorenstein toric contact manifold are related to 1. The Ehrhart quasi-polynomial of its toric diagram, 2. The Chen-Ruan cohomology of any crappant toric orbifold resolution of its corresponding toric isolated singularity, And 3. The Chen-Ruan cohomology of any monotone toric symplectic orbifold base that gives rise to it through prequantization. 10. Topological defects induced high-spin quartet state in Truxene-based molecular graphenoids. Topological defects in graphene materials introduce exotic properties which are absent in their defect-free counterparts with both fundamental importance and technological implications. Although individual topological defects have been widely studied, collective magnetic behaviors originating from well-organized multiple topological defects remain a great challenge. Here, we studied the collective magnetic properties originating from 3 pentagon topological defects in Truxene-based molecular graphenoids by using scanning, tunneling microscopy, and non-contact atomic force microscopy. Unpaired pi electrons are introduced into the aromatic topology of Truxene molecular graphenoids one by dissociating hydrogen atoms at the pentagon defects by atom manipulation. Scanning tunneling spectroscopy measurements together with density functional theory calculations suggest that the unpaired electrons are ferromagnetically coupled, forming a collective high-spin quartet state of S equals 3/2. Our work demonstrates that the collective spin ordering can be realized through engineering regular pattern topological defects in molecular graphenoids, providing a new platform for designer one-dimensional ferromagnetic spin chains and two-dimensional ferromagnetic networks.